This is another example of hypothesis testing for a mean when sigma, the population standard deviation, is known. So again, this is the process we use if the population standard deviation is known. And in this particular example, we're talking about sigma. The standard deviation for the population is 7. So because that is given to us in the problem, this is the process we can use. When that's not the case, we'll use a different process with the t-distribution in separate videos. Okay, so here in this example, we've got that the resting heart rate for adults has an average of 65 beats per minute with a standard deviation of 7 beats per minute. A pharmaceutical company wants to determine whether individuals on a particular medication have a different resting heart rate at an alpha equals 0.01 level of significance. 40 individuals are given this medication, and the average resting heart rate for this group is 62.2 beats per minute. So first of all, so you'll be answering these 3 questions. We did an example like this previously, so try to look at that to work through this. So you'll be answering the questions, is this a one-tailed test or a two-tailed test? Write the null and alternative hypothesis. Find the p-value, the probability of a result at least this extreme, assuming the null hypothesis is true. And what should the study conclude? Explain your answer in context. So pause and try this out. Take a moment, think about these, take out some paper, write stuff out, and we'll talk about it together in a moment. Okay, so we know that, so is this a one-tailed test or a two-tailed test? Here we are asking the question whether individuals on this medication have a different resting heart rate. So it's not saying do they have a higher heart rate or a lower heart rate. It could be different in either direction. And because it's different in either direction, the direction's not specified, this is a two-tailed test. And so that will come up both when we describe the null hypothesis and at the very end when we calculate the p-value. So our null hypothesis is that the mean heart rate for individuals with this medication is still 65 beats per minute, that this medication does not change an individual's heart rate. And our alternative hypothesis is that it does change the resting heart rate. So our alternative hypothesis is that the mean is not 65 beats per minute. It could be larger, it could be smaller. It's a two-tailed test. Okay, so we now want to find the p-value, the probability of a result at least this extreme, given that the null hypothesis is true. Here are our general formulas. The z-score is the sample mean minus the mean of the sample means over the standard deviation of the sample means, where the mean is just the mean assumed by the null hypothesis, here 65. And the standard deviation of the sample means is the given standard deviation divided by the square root of the sample size. So up here in the problem, we had a standard deviation of 7, a sample size of 40, and the sample mean was 62.2. So those are those values here. A sample mean of 62.2 for those 40 individuals. A standard deviation for the population assumed to be 7 beats per minute. A mean for the general population, according to the null hypothesis, of 65 beats per minute, again, assuming the medication does not change their heart rate. Then the standard deviation of the sample means is the old standard deviation, 7, divided by the square root of the sample size, divided by square root of 40, and that gives us 1.106. And again, that sample mean for those 40 individuals who were on this medication, their heart rate was 62.2 beats per minute. So our z-score then is 62.2 minus 65 over 1.106. That gives us a z-score of negative 2.53. So once we have our z-score, we now need to use either the standard normal table, the z-score table, or a computational device to figure out the probability in the normal distribution in the standard normal distribution of a z-score being, in this case, less than negative 2.53, because that would be the tail end since it's a negative z-score. So we're looking at the negative z-score chart, and we're looking for negative 2.53 in that chart. So negative 2.5 in the row and 0.03 in the column gives us a probability of 0.0057. So the probability that the sample mean is less than 62.2, assuming the population mean is 65, is equal to the probability that the z-score is less than or equal to negative 2.53, and that is 0.0057 from the table. So that's what this looks like. We're in this tail, a z-score of negative 2.53, and this tiny little probability over here, 0.0057. Okay, because this was a two-tailed test, that is not our p-value yet. We need to multiply by 2 to find the p-value. Why is that? It's because it's a two-tailed test, and we wanted to find the probability of a result at least this extreme in either direction. So here's the probability in this tail, 0.0057. Remember that the normal distribution is symmetric. So the probability on this side is also 0.0057. So the p-value, the probability of a result at least this extreme in either direction, is the total area of these two tails. That's 2 times 0.0057, which gives us 0.0114. Okay, so we have our p-value. Now, what should we conclude and explain our answer in context? So our p-value is 0.0114. It's pretty small. However, we were using an alpha equals 0.01 level of significance. So our question is always, how does our p-value compare to alpha, the level of significance? This is our symbol for alpha. And here, the p-value 0.0114 is slightly larger than alpha 0.01. And because the p-value is larger than the level of significance, we do not reject the null hypothesis. The null hypothesis was that the heart rate is unchanged for people on this medication. We're saying we don't have enough evidence to show that the medication changes the heart rate. So we do not have enough evidence to argue that this medication changes the heart rate of individuals at an alpha equals 0.01 level of significance. We do not reject the null hypothesis, and this is what we would say in context, or something we could say. Something to note, if we had been using a 0.05 level of significance, we could have rejected the null hypothesis. We would have had a p-value less than 0.05, but that's not the level of significance we were using. And the practice is that the level of significance should always be determined before the experiment is conducted. Again, 0.05 is very common, but there might be reasons to use a different one. So, this is related to someone's health, to medication. So we might want to be very confident one way or another if we're making statements. And if you want to be, if you want to be more confident, you could have a more strict level of significance like 0.01. On the other hand, if we're doing a study that is like long-term and we have a small sample size, we might know that we could at best have a 0.1, a 10% level of significance. So it definitely depends on the context. It might be about the journal that this is being written for, or it might be about how important are the consequences of your research, or how large can your sample size be. But the level of significance is determined ahead of time, usually 0.05, 0.01, or 0.1. And then we're comparing the p-value we get in the experiment to our preset level of significance.